So today we're going to be looking at the second derivative test. Now what this derivative test is going to perform is it's going to allow us to spot where those points of inflections are. This is when the graph changes from concave up to concave down. And these problems often come in two different types. They're going to come in either a straightforward problem, something where you can find the derivatives relatively easily, and when you go and calculate the second derivative, it's not going to take a long amount of time, meaning the problem should be able to be done in less than 5 minutes. If the problem is taking more than 5 minutes, that is probably going to be a style of question that you're going to be able to use technology on. Not to say that that is an absolute rule, but typically you're going to run into one of the two. So let's go ahead and take a look at the first style of problem. This is one that we won't need to use a calculator on. Now, when we're looking at this graph, what we're going to notice is that we already know the general shape of this graph. This is a fifth degree polynomial. I can go ahead and I can pull out a few zeros. The idea is that this graph is going to start moving down and come at this in some way, shape, or form. Now, it's going to have a couple bumps. In fact, because there are 5 degrees, this is going to have 1, 2, 3, and 4 bumps. So what we're looking for is I'm looking for 1, 2, 3 points of inflection where that graph changes direction. So our first step is to go ahead and calculate the first derivative. Now, the first derivative is going to allow us to find the maximum minimum points when it is set equal to 0. So f prime of x is negative 15x to the fourth plus 15x squared. So if I were to set this equal to 0, I would be able to find the points where the graph is at a local maxima or local minima. But we're not after that. What we're going to be doing is I'm going to take the second derivative, which is going to be f double prime of x, and I get negative 60x cubed plus 30x. This, when I set this equal to 0, is going to give me, boom, those 3 points. So let's go ahead and do exactly that. Set this equal to 0 and solve. The first thing you might notice is that I can factor out a 30x. So 30x, parenthesis, negative x squared plus 1 is equal to 0. This allows me to separate this into some very easily manageable chunks. My first one right here, 30x is equal to 0, which means x is equal to 0. I found one of my points of inflection. I don't know which one. I have to find the other two before I know which orientation these are in. So I'm going to set that middle term, negative x squared plus 1 equal to 0. Negative x squared equals negative 1. X squared equals positive 1. Oh, hold on. That's a 2. Which is going to be positive 1/2. Almost slipped by there. And the last step right here is I'm going to take the square root. So x equals the square root of 1/2. Or if I wanted to rationalize that, I would get the square root of 2 over 2. Both the positive and the negative version. So now I know exactly where these points of inflections are. I have one point of inflection at 0. I have one at the square root of 2 over 2. And I have one at negative square root of 2 over 2. So that's where the graph is changing. Now I can visually look at this one and say, hey, I know to the left of this value I'm going to be concave up, between these concave down, between these concave up, and at the end concave down. But let's say theoretically I don't know how to interpret said graph. Maybe the question, albeit was easy to find the derivatives of, maybe I can't figure out what the shape of this is without some sort of assistance. So what we do is we set up just a table of sorts. We're going to do this in purple. No? Yeah, why not? So I have a couple different values. I'm going to say, okay, if I have x is less than negative square root of 2 over 2, I have where x is between negative square root of 2 over 2 and 0. X is between 0 and the positive square root of 2 over 2. And then where x is just greater than the square root of 2 over 2. And I need to discuss concavity among each of these. So I have 1, 2, 3, 4 sections of the graph. Now, the way to spot what's going on is quite literally what we're going to do is I'm going to take a value and I'm going to plug it into the derivative and say, hey, what's going on here? So what's a number that's less than the square root of 2 over 2? I'm going to take my f double prime and plug in, let's say, -5. And that's going to give me an answer. Now, if I plug in -5, this is going to be a really big negative. Let's actually go ahead and do this. That's going to be 125 times 60. Let's just say really big number plus slightly smaller number. I'm going to get a positive number. So that positive number means this is concave up, which we know from the shape of the graph. The positive number signified concave up. If I plug in a number between here, now this is the square root of 2 over 2, so we're looking at something that's between 0 and that. So if I plugged in something like f of 0.1, and I actually did the math, what I'll end up getting after working this out is I will get a negative number. And so that negative number is going to give me a concave downward direction. And then as I keep moving through, and so, careful here, that's a negative 0.1 because my next one is I would plug in an f of 0.1 on the other side of 0. And if I plug that in, I will get a positive number. And again, if I plug in another number, let's say f of 5, and I work out the math, I'll get a positive, which means my graph goes from concave up to down to up to down. Sorry, that is a negative value. Down, which makes sense because the graph we see is up, then down, then up, and then down. Boom, and we get that. So we see the application is not too bad. In fact, the hardest part is going to be plugging these values in, plugging whatever test value in and saying, hey, okay, what shape is this going to make? So let's jump off onto the next one. Slightly smaller set of numbers. This might be a little easier to grasp because let's take a look at solving this. So on number 3, let's go ahead and get started. We're going to go ahead and calculate the first derivative, which is going to be a 6x minus 3x squared. And I'm going to use that to calculate the second derivative. So f double prime of x is 6 minus 6x. This is the value that I'm going to set equal to 0. And by doing that, negative 6x equals negative 6. So x equals 1. In this case, I only have one value of which I'm testing around. So I'm going to go ahead and I'm going to plug in some values where x is less than 1 and where x is greater than 1. And I'm going to see what I get. So a value that's less than 1, let's go ahead and plug in f double prime of, sorry, slowness there, f double prime of 0. And then a number greater than 1, f double prime of 2. So if I plug in a 0, 6 times 0 is 0, I get a 6, which in this case, the only thing I'm really concerned about is the positive, which means this is concave up on this side of the function. On the other side, when I plug in a 2, that becomes 6 minus 12, which is negative 6. But again, the only thing I'm concerned with is the sign, which means this is concave down. Now, this tells us a very special thing about the graph. We know it's up on the left and down on the right. So I have an upward facing graph on the left and a downward facing graph on the right. And this point right here is at an x value of 1. Which also does make sense because this is a cubic function with a leading negative, which means I have 2 bends and it ends up going downward. So, like I said, not too bad. So why don't you go ahead and pause the video, try out number 5, and see how well you do. Okay, so now that you've had a shot to try it out, let's go ahead and give this a shot. Now, with this function, one of the things that we're going to do is we're going to have to calculate the first derivative using a function rule. Not bad. I'll come over here and I'm going to write out if u is 2x and u prime is 2. Sorry. V is x plus 1, which means v prime is 1. And if I do quotient rule here, it's low d high minus high d low all over low squared. So low d high, so 2x plus 1 minus high d low, 2x times 1 all over low squared. So x plus 1 squared. So let's see, that simplifies down into 2x plus 2 minus 2x all over x plus 1 squared. And those cancel out. So my derivative is going to be 2 over x plus 1 squared. My next thing, if I want to calculate my second derivative, f double prime of x, well, again, I have a quotient, so I'm going to have to do the same thing. So if u is 2, u prime is 0. If my high is going to be x plus, or my low is x plus 1 squared, I can either use the chain rule on this, or what I could do is I could go ahead and simplify this down into x squared plus 2x plus 1, which allows me to quickly get that. There we go. And now I'm going to low d high minus high d low all over low squared one more time. So low d high is going to be that times 0, so x plus 1 squared times 0, which is going to cancel itself out, minus 2 times 2x plus 2, all over low squared, which is x plus 1 squared squared. This is going to give us negative 4x minus 4 all over x plus 1 to the 4th power. Okay, and now the big thing is we're going to be setting this equal to 0. So I'm going to go ahead and set that equal to 0, which means that as I'm solving for this, I'm really ending up with negative 4x minus 4 is equal to 0, which gives me negative 4x equals 4, x equals negative 1. Now, here's a special idea about this negative 1. If we look back at the original function, this is a rational function. I noticed that the original function cannot have a denominator of x equals negative 1 because I'll be dividing by 0. That won't work, which is where we see our point of inflection. So, albeit I have a point of inflection, what I know is that the graph itself doesn't support that as an answer, because the graph itself, let's do this in red, has a horizontal asymptote at 2 and a vertical asymptote at negative 1. The graph does not change inflection at negative 1. It has a change of inflection. So what do I mean by that? Well, let's go ahead and let's plug in a point on each side of this change of inflection and see what signage we get. So move down here just a tad. If I plug in a value, let's say f double prime of, I need to plug in a number to the left of negative 1, so negative 2. That's going to give us a, let's see, negative 2, that'll be 8 minus 4. It'll be a 4 over negative 2 plus 1 is negative 1 to the 4th power. So this is a positive number. On the right side, I'll plug in f double prime of 0, which gives me a negative 4 up top and a 1 on bottom, which is a negative number. So if I see the graph is at this point, let's see, maybe should have left some space here. So for x is less than negative 1, we are concave up. And for x is greater than negative 1, we are concave down. So if I have a concave up to the left of negative 1, I have that. And over here I have concave down. And we notice that at the negative 1, yes, it does change inflection from up to down, but not by going into a point anywhere, but by avoiding it completely in the asymptote. So there we go. So that is probably one of the more complicated ones that you'll get by hand. Again, it's not too terribly bad, which will bring us to the second page or the second set. So in this second set, what we're going to be looking at is we need to find the second derivative, and we're going to estimate the points of inflection using a calculator. Now with these, we can actually bypass the second derivative to find these points of inflection using a special little trick. And so let's go ahead and take a look. Number 7. The first derivative isn't going to be too terribly bad. Our f prime of x is going to be 2/3 x to the negative 1/3, and then the 3 disappears off. Now, this graph is all we need to find those points of inflection without having to go into the second derivative. And how do we do that exactly? Well, let's take a look. Let's pop open our calculator, and we're going to plug this graph in. So come over to our y tables, and we get 2/3 x to the power of, let's see, negative 1/3. And let's graph this. So it looks like a rather tight graph, so maybe negative 3 to 3. Okay. And so what we see is the fact that our derivative has what looks like an asymptote right here in the middle, which is going to present a slight problem. It means that we can't exactly use our super good shortcut, but I can figure out where this asymptote is. Realistically, this asymptote, as I'm looking at it, is going to be at 0. So I have both a minimum and a maximum at x equals 0. So I can skip the second derivative and say I have a critical value at x equals 0 where it changes orientation from negative to positive concavity. How do we figure that out? Well, we look at the slope of this derivative. We don't need to calculate the second. We're just going to look at the slope of the second. I see the slope is going negative. So over here in my answer key, when x is less than 0 and when x is greater than 0, again, I would normally have to calculate the second derivative to see what's going on, but not a big deal. When x is less than 0, I notice my slope is going downward. And we know a downward slope, which would mean a downward output for the second derivative, means it is concave down. And on the right-hand side, my slope, again, in this case, is increasing. Even though my slope is downward, my slope goes from a very, very steep negative to something that is approaching 0. So my slope is increasing, which means concave upward. Awesome. So we didn't even need to use the second derivative. We just bypassed it by observing the graph of the first. So why don't you pause the video, try out number 9, and see if you can bypass the second derivative by using the graph of the first derivative to reveal the information. Unpause it when you're done and see how well you can compare to this. Okay, so let's take a look at number 9. So number 9, we need to find the first derivative, which means that I'm going to have to look at this and say, okay, this is going to be a product rule. So if u is x, u prime is 1. If v is the square root of x plus 3, v prime, I'm going to have to take that power, so 1/2, multiply that, so x plus 3, I have to subtract 1, so that will be negative 1/2, and then times the derivative of the inside, so times 1. So chain rule in action right there. I take the product for the 2, so I get square root of x plus 3 plus, let's see, that's going to be x over 2 times this, which because it's negative, it's going to be x plus 3 rooted. Now here is our derivative. Now this looks a little complicated, but that's okay because again, we're going to see if we can't bypass the second derivative using just this equation. So let's take a look and see how well this compares on the graph. Let's go ahead and actually, first off, let's clear this. And I'm going to plug in this function. So I get the square root of x plus 3 plus x divided by 2 times the square root of x plus 3. Boom. Let's take a look at the graph. Cool. So I got a lot going on here. So let's zoom out just a little bit. Let's make that, oh, that might be why. Negative 10 and 10. Does that make a difference? Not so much right here. So let's zoom down a little farther. Negative 15. Okay, so now this information tells me everything that we need to know about this. Now, we know that the minimum or maximum points on this, which is going to be right here at the end, is going to be where there's a change of inflection. Now, however, when I look at this, I notice that there's not going to be a change in inflection because there's not really a minimum. There's an implied minimum. The graph looks like it could keep going. So I'm going to say, hey, there is no change in inflection because there is no minimum value. So let's take a quick look at what the original graph would look like and see how well we are. So if I have x times the square root of x plus 3. So even though my slope is decreasing, my slope is positive the entire time along this graph. In fact, let's actually go ahead and let's make our original graph a little thicker. So this is our derivative, and then this is our original graph. We notice it's concave upward the entire time because the slope of our derivative, as I write on the calculator there, is going to be positive the entire time. So if I were to take the second derivative would be positive, again, the entire time. The only quasi point of inflection would be what happens at the other side of that. So I know that there are no points of inflection. Boom. And so there's our good estimate. So let's do something a little different. Let's use one that doesn't have a root in it, but maybe square and a natural log. So our first step with this one is that we do have to find a product rule. So I'm going to have to go ahead and set up u and u prime, and then I'm going to have to set up v and v prime. So use x squared, which means that's 2x. That's the natural log of x over 4, which means that I'm going to have to look at the derivative of u, which is going to be 1/4 over this, so x over 4. So if I keep change flip, that means the 4's are going to cancel out, and I'm going to be left with x on the bottom. It's 1 over x. I then go ahead and I take the product, which is going to be 2x natural log of x over 4, plus, let's see, x squared times this is just going to leave me with an x. Okay, and so let's take a look at this graph and see if we can't use this graph to bypass the second derivative. So let's go ahead and make sure our zoom is good, and then go ahead and clear some of these out. Oh, perfect. So let's type that in. We're going to have 2x times the natural log of x divided by 4 plus x. So let's take a look at that graph. So this is our derivative right here, which I notice that it does have a minimum point, which is going to allow us to bypass that second derivative because that's going to save us a ton of time. Let's actually have the calculator graph a minimum value. Left bound, right bound, guess. So I have a minimum value at 0.8925. So there's our critical value, equals 0.8925. We can then use that to set up what's happening when x is less than and when x is greater than 0.8925, 0.8925. Should have left more room over there, but I'm just going to go ahead and separate this like that. And so let's take a look at the slope. When x is to the left of 0.8925, my slope is downward, which means that I'm going to produce a negative, which means this is concave down on the parent function. On the right side of the graph, my slope is upward, which means I will produce a positive second derivative value, and that means that it's concave up. And so let's go ahead and take a peek and see if at 0.8925 my graph switches from concave down to concave up. And so let's go ahead and plug in the original graph and see how close were we. So x squared, natural log of x divided by 4. And just to keep this separate, I'm going to make this a thick one. And so we can see, yes, that is the case. So let's set that from 0 to, we're only going to 0.89, so how about that? -5 to, I'll set that to 1, because it looked like it did it below there. And so we have a graph that looks like it's concave down. And actually, let's zoom over just a little bit farther. And that's the derivative graph, where we found the minimum point. So I should see a change in inflection, right there. So we see the fact that the graph is, in fact, concave down, and then as it moves over, it turns into a concave upward graph. Perfect. So now that we've seen that in action a few times, why don't you go ahead and try out number 13. Pause the video, unpause it when you're done, and see how well you can compare. You can either try and find the second derivative by hand, or you can try and bypass it by using that min-max trick. Okay, so let's take a look now that you've had a shot at number 13. My first derivative is going to be, let's see, cosine of x, that's going to give us negative sine x minus 1. Now, I could find the second derivative. In fact, this wouldn't be too hard to do, but we're trying to keep in the spirit of things, and we're going to use this equation. Let's zoom out just a bit. We're going to use this equation after we clear all this stuff. And find the minimum maximum points. So negative sine x minus 1. And our window is only from 0 to 4 pi. Awesome. So this is our derivative. Looks like we don't go below, probably negative 4. So let's set the y max to, negative 4 and to 1. Just gives us a better view. Okay. So now each one of these points, I want to figure out what their value is so that I can set them as our critical value. So it looks like I have 1, 2, 3, 4. So I know I have 1, 2, 3, 4, which fortunately and unfortunately is going to give us 1, 2, 3, 4, 5 different intervals. So when x is less than the first one, when x is between 2, between 2, between 2, 1, 2, 3 betweens, and when x is bigger than the last value. So let's calculate our minimum. So I have a left bound, a right bound, and so this is going to be at 1.57. You should recognize that number because that number is pi over 2. Not that we need it, but now that we found a minimum, let's find a maximum. So left bound, right bound guess. And so we have 4.71, which if you recognize that is going to be 3 pi over 2. Let's calculate the next minimum. Left bound and right bound produce 7.853, which you should recognize as 5 pi over 2 at this point. And you should recognize that the next one is going to be 7 pi over 2. But we're going to keep in the spirit of things and trying to utilize this nice little trick. Left bound, right bound, which is 10.995. Perfect. So when x is less than 1.57, when it's between 1.57 and 4.71, 4.71 and 7.853, 7.853 and 10.995, or when x is bigger than 10.99. We're going to check out the points of concavity simply by looking at the slope. I notice the slope on the left is down, which means I'm going to produce a negative number, which means it is concave down. And then I produce a positive, a negative, a positive, and a negative. Boom. And so there are our values. We could check this by graphing our first one and see if it changes inflection in each one of these. So if it's every pi over 2, let's go ahead and take a peek at that. So let's set our new function equal to the cosine of x minus x. We got our window from 0 to 4 pi, but let's set the interval at pi over 2. I don't know what the min-max is, so let's set it from negative 10 to 10. So there's our derivative. Boom. So what we notice is the fact that our derivative is concave down, concave up, concave down, concave up. And we assume that that graph, if I set a lower y min, let's say negative 20. We should see that graph or that trend continue all the way down. Flattens out and then keeps going. So boom. There we go.